Hello everybody, welcome to this session. In this session, we're going to discuss a very important concept, that is photoelectric effect, which is very much useful for your board exams as well as any sort of competitive examination, be it JEE Main, JEE Advanced, NEET, PITSAT, CUET, or even SAT. For all kinds of these entrance examinations, this concept is very much important. So please be ready with your pen and paper. Here we go in detail about photoelectric effect. What is photoelectric effect? So it's all about the emission of electrons from metals when radiation falls on the metal surfaces, right? So how are these electrons emitted from the metal surfaces? When you consider metal, there are many electrons in it. Some are bound to their parent atoms, and some electrons are not bound to the parent atoms. They are free to move throughout the metal, throughout the material. So those electrons are called free electrons. See, these free electrons are bound to the material by some energy. See, inside the material, these electrons will have potential energy less than the electrons when they are outside. In case if these electrons can get the energy by any means, then they can come out of this metal surface. That process is nothing but photoelectric effect. Understood? Right. So first we need to know about the free electrons. So free electrons in metals. See, metal contains many electrons, and the electrons that are weakly bound to the atoms can move throughout the material, and upon supply of sufficient energy, these electrons can be pulled out of the metal. Okay, so before supplying that energy, these electrons are bound to that material. They are free to move within the material but can't escape out of the material at room temperature. See, varies with temperature even. When temperature is increased, usually these electrons gain the thermal energy. By that means also they can be emitted from the metal surface. Understood? Yes. Now, in order to bring this electron out of this metal, some minimum energy is required. Upon supplying minimum energy to these electrons, they can be released from this metal surface. When electrons are bound to the metal, upon supply of the energy, minimum energy, we can get these electrons out of the metal surface. So that minimum energy required is known as its work function. See, work function is the minimum energy required to release an electron. This energy is very less, so usually it is expressed in terms of electron volt. So the minimum energy required to make a free electron escape from the metal surface is known as work function, denoted by W0, or sometimes it is expressed as phi. Phi represents the work function and its unit is electron volt. See, when light falls on a metal surface, light carries energy, right? So if that energy is imparted to the electron here, and if that energy is sufficient enough to get this electron out of it, then electron is ejected out of the metal surface. So that minimum energy required, remember it is only minimum energy required to remove the electron from the metal surface, is known as its work function. So work function varies from metal to metal. Different metals will have different work functions. Understood? All right. now. See, coming to the electron emission, the different ways in electron emission. See, electrons are ejected from the metal surface by some means. The phenomenon of ejection of electrons from metal surface is known as electron emission. So there are different ways for the emission of electrons. The first one is thermionic emission. As I said, when temperature is increased, that means when a metal surface is heated, the electrons gain the thermal energy. When sufficient thermal energy is imparted to the electrons, they can come out of the metal surface. This process of emission of electrons is known as thermionic emission. Another one is by applying strong electric field. That method is called field emission. So field emission is the process of releasing of the electrons from metal surface when very strong electric field, that is in the order of 10 power 8 volt per meter, very high electric field. When such fields are applied to a metal, the electrons can be pulled out of the metal. And especially in spark plugs in the automobiles, the same thing happens. So that process is field emission. Is that clear? Right. Now the third one is a concept for the day, that is photoelectric effect. So in photoelectric emission, emission of the electrons takes place. It is electron emission by any means, thermionic emission or field emission or photoelectric emission. It is about the electron emission. But in this particular case, photoelectric emission, the term photo stands for light. When light of suitable frequency illuminates, or when light of suitable frequency falls on a metal surface, electrons absorb that energy of the light and they can come out of the metal surface. This process is called photoelectric emission. Right. See, if light is able to release the electrons from a metal surface, that means light carries energy. What are there in this light? See, light contains energetic particles, photons. Right? Now let us learn about these photons. In an electromagnetic wave, electric and magnetic fields are oscillating perpendicular to each other, and also they are perpendicular to, their oscillation is perpendicular to the direction of wave propagation. You might have studied about the electromagnetic waves, right? So these electromagnetic waves carry energy in the form of photons. Photons are present in electromagnetic waves. In fact, light is also an electromagnetic wave. Then its energy density of the electromagnetic wave, energy contained per unit volume, that is energy density, energy per unit volume, that is given by U is epsilon naught E RMS square, root mean square value, E RMS, which is E naught peak value by root 2. It's a square. So it becomes E maximum square by 2. Understood? So E RMS is EM by root 2 squaring epsilon naught E RMS square is epsilon naught EM square by 2. That represents the energy density, energy contained by an electromagnetic wave per unit volume. Now from this relation, it is clear that energy density is proportional to square of the amplitude of the electric vector, see E RMS square or E maximum square. It is directly proportional to the square of the amplitude of the electric vector. That means more energetic wave will have larger amplitude. More the amplitude, more is the energy possessed by the wave, electromagnetic wave. Now, see, here are 3 different electromagnetic waves, keeping the wavelength fixed. For all the 3, wavelength is same. But see, their amplitudes are different. All the 3 waves have different amplitudes. Now clearly energy carried by the third wave E3 is greater than E2 and that is greater than E1. If energy is more, even their energy density will be in the same proportion. Understood? Yes. The energy of electromagnetic wave, energy of an electromagnetic wave is an integral multiple of quantum of energy. That quantum of energy is nothing but photon. It was proposed by Max Planck in the year 1900. Any energy associated with an electromagnetic wave is an integral multiple of quantum energy of the photon. So that's why we say E is proportional to nu. E is directly proportional to nu. E is equal to h into nu, where h is Planck's constant. Okay. Next. So coming to the properties of these photons. Photons travel with the speed of light, which is 3 into 10 power 8 meter per second. And photon is nothing but a packet of energy emitted from a source of radiation. The photon is shown here. Okay. Photon is nothing but a packet of energy. And it is emitted from a source of radiation. All these photons travel with the speed of light, which is 3 into 10 power 8 meter per second. All the photons. The energy associated with a photon is given by E equal to h nu. And we have the relation C is equal to nu into lambda. So for that, we can write nu as C by lambda. That's how h nu would become hc by lambda. And also from Einstein's mass energy equivalence, we have E is equal to mc square. So E is h nu equal to hc by lambda, or that can be taken as mc square, where m is mass of the photon, dynamic mass of the photon. The rest mass of the photon would become 0. Here nu is the frequency of radiation, lambda is the wavelength of radiation, h is Planck's constant, and m is the dynamic mass of a photon, whereas its rest mass is always 0. Okay. Now, coming to the energy associated with a photon of wavelength lambda, we have E is equal to hc by lambda. See, coming to that relation, E is equal to hc by lambda. This is in joule. To convert it into electron volt unit, you need to divide it with charge of electron. So it becomes hc by E into lambda. Here, except lambda, remaining 3 are constants. H is a constant, Planck's constant, which is 6.625 into 10 power minus 34 in joule second. SI unit. C is the speed of light, which is 3 into 10 power 8 meter per second. And E, charge of the electron, which is 1.6 into 10 power minus 19 in Coulomb. Except lambda, the remaining 3 are constants. Substituting these values and simplifying, you'll get it as 12,400 by lambda measured in angstrom unit. That energy is in electron volt. Or if lambda is in nanometer, then it would become 1240 as given here. 1240 by lambda. Lambda is measured in nanometer. The energy unit is electron volt. So remember these two relations. Directly energy related to the wavelength. E equal to 1240 by lambda in nanometer, or E is equal to 12,400 by lambda in angstrom. That energy is expressed in electron volt. Okay. Now, the dynamic mass of a photon is given by, from the relation E is equal to mc square. We have E is equal to mc square. From that, m is E by c square, right? And E is h nu, so h nu by c square. Whereas nu by c is nothing but 1 by lambda. From the relation C is equal to nu lambda, nu by c, 1 by lambda is nu by c. So it can be written as ms, written as h by lambda into c. That mass is called the dynamic mass, whereas its rest mass is 0. When photon is at rest, its mass appears to be 0. What is the momentum of the photon? Momentum, simply it is the product of mass and velocity. So for a photon which is moving with speed of light, if its mass, dynamic mass is m, its momentum is m into c. Now from the relation E equal to mc square, which can be written as E equal to mc into c, this mc is nothing but momentum. So momentum is E by c, E by c, where E is h nu by c. Now again, for nu by c, you can write it as 1 by lambda. So that's why h becomes equal to, p becomes equal to h by lambda, or lambda is h by p. That's what is de Broglie's concept, de Broglie's equation, which relates the particle nature here, which is momentum, to the wave nature of the radiation, that is in terms of its wavelength lambda. Understood? So particle nature and wave nature are related to each other, proving that radiation exhibits dual nature. At times it acts as particles, at times it acts as waves. Photons are electrically neutral. They do not carry any charge. They are neither positive nor negative. They are electrically neutral. That's the reason why they are not deflected by either electric or magnetic fields. They do not respond to the electric as well as magnetic fields because they are electrically neutral. Now, the power of a source of electromagnetic radiation. What is power? It is energy per unit time. So the power is given by n times h nu, as E is equal to h nu or hc by lambda. When there are n photons emitted per second, that capital N is number of photons emitted per second. Then nh nu would become power, because it is per second, energy per second. Energy per unit time is nothing but the power expressed in watt. Once if you are clear with the term power, there is another term related to these sources, electromagnetic radiation sources, that is electromagnetic waves will have certain intensity even. Intensity, where intensity is defined as energy per unit area per unit time. The intensity is energy per unit area per unit time. Energy per unit time is power. So intensity can also be expressed as power per unit area. Power per unit area, or energy per unit time per unit area. Okay. Now coming to the units, it is measured in watt per meter square. Power is watt. Power per unit area is intensity, watt per meter square, expressed as nh nu or nhc by lambda. Here n is in lower case. Okay. Whereas this n represents number of photons incident per unit area per unit time. Okay. The relation between n in uppercase and n in lowercase is n is equal to total number of photons divided by area of cross section. That is the intensity of electromagnetic radiation. So the intensity of electromagnetic radiation in vacuum is expressed as half epsilon naught E square C. E naught represents the peak value. E naught is peak value. It is completely expressed in terms of electric vector. The same can be expressed completely in terms of the magnetic vector as half B naught square C by mu naught, where mu naught is the permeability of free space, epsilon naught is the permittivity of free space, or the intensity can also be expressed as E naught B naught, the peak values of electric and magnetic field vectors divided by 2 mu naught. Okay, that is the intensity of the electromagnetic radiation. Remember here the ratio of E naught by B naught, E naught to B naught ratio is same as E RMS to B RMS ratio. So in this equation, E naught is the amplitude of the electric vector measured in volt per meter. B naught is the amplitude of magnetic vector measured in Tesla. C, as usual, it represents the speed of light measured in meter per second. Okay. Now the relation between E naught, B naught, E RMS, B RMS and the speed of light is given here. E naught by B naught. This ratio is same as E RMS by B RMS. And this ratio is always equal to speed of light. Very much useful and very important relation between E, B and C. Electric field vector, magnetic field vector and the speed of light. A photon may collide with a material particle like electron. Okay, but in such collisions, its momentum as well as energy both are conserved. Energy conservation as well as conservation of linear momentum are valid in case of collisions of photons with the material particles like electrons. Okay, now coming to the photoelectric effect. So far we have learnt about the basic that is necessary to understand the photoelectric effect concept. Okay, photoelectric effect is caused by radiation, but what are there in the radiation? Photons are there. What are the properties of these photons? What is a photon? How does it carry energy? What is its intensity? What is its power? All that we have discussed now. Now coming to the photoelectric effect, it is the phenomenon of emission of electrons when radiation illuminates the surface. Okay, this phenomenon is known as photoelectric effect. See, the ejected electrons in photoelectric effect are called photoelectrons. The electrons ejected from the surface of a metal are known as photoelectrons. Okay. Now, what is its experimental setup? See, here is a metal plate which emits the electrons. The source of radiation. Radiation falls on the metal plate passing through a quartz window. Then metal plate releases the electrons. These electrons are collected at this plate C, nothing but anode. Collecting anode it is. And as these electrons are passing through this circuit, it constitutes a current, but the current magnitude is very small. So to measure that current, here is a microammeter. The current magnitude is very, very less, in the order of 10 power minus 6 ampere. So that's what is microampere. Now to measure the potential difference between the metal plate and the collecting anode, here is a voltmeter. And the potential between these two, the plate and the collecting anode, can be varied by using this battery with the help of a rheostat. Okay, so these are the different parts. These metal plates, plate which emits the photoelectrons and the plate anode which collects the electrons, are enclosed in a glass tube, evacuated glass tube. Q is the quartz window, T represents the evacuated glass tube, P is the photosensitive metal which releases the photoelectrons, C is the collecting anode, S, here it is, S is the source of radiation, B, high voltage battery it is. This is a high voltage battery. A represents microammeter and V is the voltmeter. This V is the voltmeter. Now, let us check the experiments, experimental observations of this photoelectric effect. See, the metal plate P is earth to zero potential. P is connected here. This is earth connected. So its potential can be maintained at 0. Relative to the plate P, the collecting anode can be maintained at a desired potential, either positive or negative. This plate can be made positive or negative with the help of this slider here. Okay. So C can be maintained at a desired potential, either positive or negative. Voltmeter between these two measures the potential difference between P and C. And if there is any current passing through this, that is measured by the microammeter. When UV radiation falls on plate P from this source S, the radiation excites the electrons in the metal plate, and if the electrons gain sufficient energy, or if it is more than or equal to the energy with which they are bound to the metal surface, then there is an every possibility for this electron to get ejected from the metal plate. Now these electrons will move towards the collecting anode, constituting current. That current is measured by this microammeter. Understood? The experiment, photoelectric effect experiment. Now, let us see the effect of intensity of light on photoelectric current. Intensity of light. Already we have defined what is intensity. So the intensity is nothing but the energy that incidents on a surface per unit area of cross section in unit time. See, UV light of particular frequency decides the energy of each photon, as E is equal to h nu. Related to this frequency, energy is fixed. When these photons are allowed to fall upon the metal plate, the metal plate can release the electrons. Now, the anode is made positive with respect to P. Anode is maintained at a little higher potential so that it can collect the electrons ejected. See, electron is a negatively charged particle, right? If you make this terminal positive, these negative charges will move towards the positive terminal, anode. Okay, that's how collection of electrons takes place at the anode C, constituting current. Now, what is the effect of intensity? That's what we're going to discuss. To measure the effect of intensity, or to understand the effect of intensity, keep the frequency and accelerating potential fixed. Fix the potential difference between metal plate and the collecting anode. Also, fix the frequency of the incoming radiation. Then alter the intensity of the radiation. Here, intensity represents the number of photons. More the intensity means more is the number of photons that are falling on the metal surface. If more photons are falling on the metal surface, they can release more electrons. So, proportionally, current increases with increase in intensity, isn't it? Right. When intensity is increased, more number of photons hits the surface, thereby releasing more number of electrons, and these electrons are collected by the anode. More the electrons means more is the current established in the circuit. So number of photons ejected from this photosensitive plate is proportional to the intensity of radiation. So direct relation, it is directly proportional. So the graph here represents the relation between photoelectric current on the y-axis and intensity of light on the x-axis. See, with increase in intensity, the photoelectric current also increases linearly. It is linear relationship. So from this we can say that photo current is directly proportional to the intensity of incident light. More the intensity, more is the photoelectric current. Okay. Remember, intensity is not going to increase the energy of individual photons, but intensity increases the number of photons that are falling on the metal surface. So more the number of photons, more is the possibility for the ejection of, it is the possibility of ejecting more electrons increases. So that we'll get more current. Clear? Now, coming to the effect of potential difference on photoelectric current. The previous one is effect of intensity. Now, what happens if potential difference between P and C are altered? Potential difference is altered between P and C. See, depending upon the polarity of potential maintained between photoelectric plate and the anode, there are two possibilities, two situations may arise. When plate is maintained at higher potential compared to anode, or when anode is maintained at higher potential compared to the plate. First one, anode is maintained at a higher potential compared to the plate. Vc minus Vp is greater than 0. That means Vc is greater than V of the plate. Potential of the anode is more than the potential of the plate. That particular potential will help the electrons to move towards the plate. So that's why it is called accelerating potential. It accelerates the electrons that are released from the metal surface. Understood? Now, see, collecting anode is kept at higher potential, positive potential compared to the photoelectric plate. In this case, frequency and intensity are maintained constant. See, we are going to study the effect of potential difference on photoelectric current. So keep the other two parameters, the frequency of radiation and intensity of radiation, these are maintained constant. Now potential difference is varied. See, if the potential difference is varied voltage, with increase in voltage, the photocurrent gradually increases up to certain value, and after certain potential, the current almost becomes constant. This constant current is called the saturation current. Saturation current. But surprisingly, even when the potential difference between P and C is 0, potential difference between P and C is made 0. That means both are maintained at the same potential. Vp is equal to Vc. Even then, see, current is not 0. There exists some current in the circuit. Why so? That we have to answer. Einstein answered all these queries. Let us discuss all those points. Follow it carefully. Right. When potential difference is varied, electrons ejected from the surface of the metal has a distribution of kinetic energies ranging from 0 to a maximum kinetic energy. Now the electrons with maximum kinetic energy will reach the anode, constitute this current. Though there is no potential difference between the metal plate and the anode is not collecting forcibly the electrons, but the electrons with high kinetic energy are moving towards the anode, constituting this current. Now, if you increase the potential of the anode, it acts as accelerating potential and attracts the other electrons also. So, there is an increase in the current. After certain potential, there is no further increase in current. This is because all the electrons are collected by the anode. There are no more electrons left that are released from the metal surface. So that's why there is no further increase in current. Only the electrons with kinetic energy, high kinetic energy, will be able to reach the anode, and that constitutes or contributes to the current here. Upon increasing the potential, the remaining electrons, the electrons with low kinetic energy or electrons with even zero kinetic energy, are accelerated towards the anode, constituting photoelectric current. When all the electrons are collected by the anode, even the electrons with zero kinetic energy are collected by the anode, there is no further scope for the increase in current. The same current will be maintained. That's what is the saturation current. When an anode is kept positive, at positive potential, more and more electrons get pulled towards this anode, causing increase in the photoelectric current. Okay. After a particular value of this accelerating potential, there is no further increase in the current because all the released electrons are collected by the anode. So current reaches a saturation value, a constant value. That particular current is called saturation current. Saturation current. Now, beyond this, even if you increase the potential is increased to this value, or even this value, at all these values, there is no further increase in current. Current is maintained constant. Even if the accelerating potential is increased, there is no further increase in the current. Now, what happens if you reduce this potential moving on this side? Moving to the left, potential difference decreases, and at this point the potential difference between P and C, that is between the plate, photoelectric plate, and the collecting anode becomes zero. Even then you can observe some non-zero current. This is because of the electrons with high energy, they are able to reach the anode even when there is no accelerating potential. Now, what happens if you reduce the potential to the negative value? That is called decelerating potential. This potential decelerates the electrons, not going to accelerate the electrons. Now, this negative potential will try to stop the electron movement towards the collecting anode. That's what is Vc minus Vp is less than 0, or you can say Vc is less than Vp. Potential of collecting anode is less than the potential of the metal plate. So in this case, when the plate is made negative, current decreases. Why is this decrease in current? Because the electron movement is prevented by the negative potential. The repulsion occurs between anode and the electrons because both are negative. So there is a decrease in the current value, and it reaches a particular value 0 at some negative potential. Photocurrent gradually decreases and becomes 0 here. That particular potential at which photocurrent becomes 0 is called the stopping potential, because it is going to stop, this negative potential is going to stop all the electrons. Even the fast moving electron is stopped by this negative potential. See, when you increase the negative value gradually, current decreases rapidly till a sharply defined negative potential V0 at which the current becomes 0. Current value, this is photocurrent, that becomes 0 for some negative potential. That negative potential is called stopping potential or cutoff voltage. Okay. So that is called cutoff voltage, cutoff potential, or stopping potential, at which even the fast moving electron is stopped. Fast moving electron or electrons with high kinetic energy are also not able to reach the anode because of its high negative potential. That particular potential is called the stopping potential because it stops the fast moving electrons even. Clear? So when potential difference is 0, current is not equal to 0. Upon increasing the potential difference on the positive side, accelerating potential, current gradually increases up to certain value. After a particular potential value, the current becomes almost constant, saturation current. When negative potential is applied, that is decelerating potential, for the decelerating potential, current gradually decreases and reaches a value 0. Okay. That particular potential at which the photoelectric current absolutely becomes 0 is known as cutoff potential or cutoff voltage or stopping voltage, stopping potential, denoted by V0. Okay. So when retarding potential is V0, current becomes 0. that is shown here. So what happens at this V naught? These electrons cannot move towards the anode because it is made negative. Between negatively charged electrons and this negative plate, there is a repulsion, and that repulsion is in such a way that is dominating the kinetic energy, or it is able to stop the fast moving electron because of its high kinetic energy towards the anode. So it is not accelerating potential but decelerating. There can be some electrons that are released with high kinetic energy. Even this electron moving with high kinetic energy towards this collecting anode is stopped by this negative potential applied here. Okay, so when this electron with high kinetic energy is stopped, there is a change in kinetic energy. From work energy theorem, we know change in kinetic energy is equal to work done. So work done by this negative potential will become equal to the change in kinetic energy of the fast moving electron. So maximum kinetic energy can be given as EV naught. Ke max will become EV naught. EV naught here represents the work done. Work done in stopping the electron. Ke max, that is the difference in the kinetic energy. Initially it has kinetic energy Ke max, finally it is stopped somewhere here. So change in kinetic energy is Ke max. Okay. What is kinetic energy? It's half mv square. Ke max means half m v maximum square. That becomes equal to EV naught. So from this, you can take the maximum velocity Vmax as root 2 EV naught. V naught is the accelerating potential by m. That will be the velocity, maximum velocity of the electron, which is root 2 EV naught by m, where V naught is the stopping potential. M is the mass of the electron and E is the charge of the electron. Understood? Yes. So until the retarding potential attains a value V naught, there is a small magnitude of current as shown here in the graph. Once it reaches the potential V naught, negative potential V naught, the current drops to 0. At V naught, no electron is able to reach the anode. So if there are no electrons flowing through the circuit, no current is established. Microammeter reads 0. So photoelectric current becomes 0 at V naught, the negative potential. That is called stopping potential. Now, what happens if you use radiation with a different intensities, low intensity and high intensity radiation, keeping the frequency fixed? See, same frequency. If the experiment is repeated with light of same frequency means energy carried by the photon remains the same, as E is equal to h nu. When nu is fixed, E is fixed. Incoming energy is fixed. Okay, but intensity is varied. Intensity means the number of photons is varied, but not the energy of each photon. Right? When radiation with high intensity is used, the saturation current is found to be greater because high intensity, that means more number of photons are falling on the metal surface, which leads to release of more number of electrons. So more is the number of electrons, more will be the current. So that's why for high intensity, we have high saturation current. When the intensity is reduced, it doesn't mean that energy of each photon is reduced. Photons are of same energy, but the number of photons is decreased. When this number of photons is decreased, there is less current released, less current established in the circuit because less number of electrons are released. So that leads to low saturation current. Okay. So stopping potential is independent of intensity. For both, you can see the stopping potential that is same. Saturation current is varying. What about the stopping potential? Stopping potential is same for both the radiations because their frequency is same. So stopping potential is independent of the intensity of the incident light provided frequency is maintained same. So it is clear from this observation that stopping potential depends upon frequency but not intensity. If you alter the frequency, if you increase the frequency, energy of the incoming radiation increases. So more energetic photons will impart more kinetic energy to the electrons. In order to stop these electrons with more kinetic energy, more negative potential is required. So stopping potential V naught will be proportional to the frequency of radiation. If this is fixed, V naught is also fixed. That's why for two different intensities with same frequency, the stopping potential remains same. Understood? Now, another effect of frequency on stopping potential. What is the effect of frequency of radiation on stopping potential? That's what we have discussed just now. See, if the experiment is repeated with different frequencies, keeping saturation current same means intensity is maintained constant. Saturation current depends upon intensity, no? Intensity is maintained constant, but frequency is altered. So if frequency is altered, obviously the stopping potential also changes. Because stopping potential is directly proportional to the frequency of radiation. The graph looks like this. See, three different radiations, three different frequencies, but same intensity. As it has same intensity, saturation current is same for all these three radiations. But see the stopping potential minus V naught 1, minus V naught 2, minus V naught 3. 3 is for frequency of high, the radiation with high frequency, nu 3. Nu 3 is greater than nu 2, where nu 2 is greater than nu 1. Proportionally, V naught 3 is more than V naught 2, which is more than V naught 1. So with increase in frequency, the retarding potential also increases. But as long as the intensity is maintained constant, the saturation current remains same. Saturation current remains same for all the three radiations. Okay. So same graph, the graph between stopping potential and the frequency of radiation, nu 1, nu 2, nu 3 on the x-axis, stopping potentials are taken on the y-axis. So it is a straight line graph passing through a point here on the frequency axis. Stopping potential becomes 0 for certain frequency here, right? That is called the threshold frequency. Beyond this point on the negative side, on this side, here, there is no photoelectric emission taking place. Metal plate is not going to release any electrons. That's why there is no potential required to stop these electrons. Stopping potential becomes 0. For certain frequency, nu, that is called a nu naught, and that nu naught is known as threshold frequency. As the frequency of incident light is increased, means going this way. The kinetic energy, maximum kinetic energy of the ejected photoelectrons is going to increase. And with increase in kinetic energy, the stopping potential is also going to increase this way. Stopping potential increases with increase in frequency. Now, from the relation work energy theorem, the stopping potential is V naught, then work done is EV naught, which is equal to change in kinetic energy. EV naught is equal to maximum kinetic energy change. So the magnitude of stopping potential increases as the frequency of incident light is increased. With increase in frequency, kinetic energy is going to increase. With kinetic energy, increase in kinetic energy of the electron, the stopping potential also increases. Understood? So on reducing the frequency, there is a minimum frequency, that is nu naught, for which stopping potential becomes 0. So if the frequency is less than this particular value nu naught, metal is not going to emit any electrons. So that particular frequency is called threshold frequency. Threshold frequency. Now, the frequency of incident light exceeds the threshold frequency, then immediately, spontaneously, the photoelectric emission takes place without any time lag. The time taken for this is roughly 10 power minus 9 second. That means within a time of nanosecond or even less than that, photoelectrons are ejected whenever this frequency crosses this particular threshold frequency. So if the frequency of incident light exceeds the threshold frequency, photoelectron emission starts instantaneously, right? Even if the incident light is dim. Dim means it is low intensity. What does it indicate? The low intensity light? It is the light with less number of photons, but not related to the energy of each photon. Dim light also possesses photons. If these photons possess sufficient energy to release the electron, photoelectric emission takes place. Okay? But dim light or light with low intensity indicates there are less number of photons, which causes less number of electrons emission. Clear? Yes. Now, let us discuss some important points that we have discussed so far. Let us recall those points again as timely points. Intensity is nothing but energy of light per unit area per unit time. That is called intensity of light. Intensity is nothing but number of photons incidenting on a surface per second, number of photons. More the number of photons, more is the number of electrons ejected. So intensity is nothing but number of electrons per second. More the number of electrons, more will be the current. So intensity is directly proportional to the current. Follow this relation carefully. Intensity indicates number of photons. More the number of photons, more is the number of electrons released. Less the number of photons, less is the number of electrons released. So photons number and electrons number is proportional. I am not saying they are equal. Every single photon may not be able to release the electron, but there is proportionality. More the number of electrons, more is the current. So electrons number is directly proportional to the current. That means intensity is related to the current. So this current is inversely proportional to square of the distance of the source from the metal source, metal plate. Okay. D is the distance between source of radiation and the metal surface. So from this, current and distance are related to each other as I is inversely proportional to D square. From that, I1 by I2 is equal to D2 square by D1 square, where I is the current flows in the circuit, photoelectric current, and D is the distance between source of light and electron emitter, source and the metal plate in this case of photoelectric effect experiment. Understood? Remember that relation, that is very much useful for competitive examinations. Another important observation here is stopping potential does not depend upon the distance between emitter and the collector. Between emitter, that is P in our experiment, collector is C, the metal anode. So it does not depend upon the distance between these two, the stopping potential. Anyway, the distance between these two is completely evacuated, right? So stopping potential is independent of this distance. Photoelectric emission is an instantaneous process without any apparent lag. The time lag is almost 10 power minus 9 seconds or even less than that. When the incident radiation is made extremely dim. Dim indicates low intensity, low number of photons, less number of photons. But the photon energy may be sufficient enough to release the electron from the metal surface. Next. See, UV light, ultraviolet light causes photoelectric emission from any metal surface. Ultraviolet light can cause photoelectric emission from any metal surface. But visible light within the range from violet to red, visible light causes photo emission only from alkali metals. Note that difference. Make a note of this point in your notes. UV light can cause photoelectric effect from any metal surface, but visible light can release the electrons from alkali metals only. Understood? Now, once again recalling work function. Work function is the minimum energy needed to remove the least tightly bound electrons. Least tightly bound electrons require least energy. That least energy is known as work function. So the work function represents the energy needed to remove the least tightly bound electrons from the surface. It depends only on nature of the metal and is independent of any other factors. Clearly remember, work function phi depends upon the nature of the metal. So different metals will have different work functions. Different metals will have different work functions. Work function is purely dependent on the nature of the metal. Understood? So with this, let us conclude this session here. The remaining will be continued in the next session. Don't miss that session. As I told you at the beginning, this is a very, very important concept for all types of competitive examinations as well as your board exam. Okay? Right. Thank you for watching. See you in the next session.